Well, certainly a pleasure to be here, and I'd like to sort of go through an evolution that we've been going through in the projects that we've done at Pacific Northwest National Laboratory. We started as really full graph people looking at building a graph database with unstructured data and then providing graph methods in order to search and identify patterns in that data. And over the last few years, we've sort of, I would say, modified or evolved our thinking, and now we really are firm believers that you really need a combination of both tables and graphs if you're going to do the complex workloads and analysis that people are doing. And so we've been busy trying to understand, how we ingest that data, how do we provide language features in order to develop both a table view and a graph view of the data, and then platforms in order to provide both table operations and graph operations so that people can do, composite, complex analytics that they want to in an integrated fashion. So let's just do a couple of quick slides. Why are graphs? Why graphs? Well, they're good for representing unstructured data. In this example here, I've got two pieces of information. Perhaps these are two emails or conversations. One talks about Mary and Sally and a 6-year-old daughter and a Christmas present, and the other one talks about Sally and a renting Joe's condo in Hawaii. And if I try to put the first one in a table, I have a bunch of columns that are pertinent to that piece of information, but I have a lot of empty spaces, and then when that second piece of information comes in, I've got all the wrong columns, and I've got a mess on my hands trying to extend the data structures I have at the foundations of my database in order to handle the new information. And so that's why tables aren't particularly appropriate when we have unstructured data, and particularly when we don't know what that data will be. So it's data that we don't own. It just comes in from maybe the internet or from collection systems. But if I put that in a graph, or I have a graph data structure at the bottom of my platform, then I can easily represent just the data I have on the first piece of information in terms of nodes and edges that are typed. And then when that second piece of information comes in, I can easily extend that graph data structure with additional nodes and edges, and I don't have to disrupt what I had there previously and copy everything. So graphs are very good at that, and that's why people have been looking at graphs or promoting graphs for unstructured data analysis. Graphs are also good at patterns, right? If I'm trying to find attack patterns in cybersecurity, or maybe a supply chain and operational development series of both materials and operations, or if I'm looking at maybe in medical fraud, looking at the relationships between doctors and hospitals and procedures, I can, if I can figure out the pattern I want to look for, I can write it down, and then I can execute some sort of constrained graph isomorphism on my graph database and find all instances of the pattern and then return that to the analyst. So it's good for visualization. Humans think like this. There's lots of literature on fast graph isomorphism applications. And so it's easy, again, to represent this as a graph, view it as a graph, and then operate it and process it as a graph. Well, if you try to do this in terms of tables, you end up with a lot of table joins, which are very expensive, consume memory, produce a lot of useless results, which you then throw away through select operations. So it's a very cumbersome process to do these types of pattern identification processes as table joins and in table operations. So this is why we were pretty much committed to doing graphs and looking at graphs as a way to process this type of information. But as we got more deeply into it, we realized that a lot of the data is structured and it is dense. On that previous slide where we had Mary and Sally, they have probably records which detail where they live and where they went to school and their addresses and things like that. And that data appears in databases. It's dense, it's structured. And that's not very easily represented with graphs. So when I do have structured data, for example, here's some net flow data, I end up with this problem of starification if I represent that dense data as a graph, where I have a single entity and then all the attributes of the data form little nodes around it with additional edges. So again, I end up using a lot of memory and obfuscating any patterns that I may want to find. The other problem is that edges, such as the producer edge there, may have attributes of their own, such as quantity and price, and I have no good way to represent that without some sort of structured data type. And then finally, if I have graphs, I have very inefficient select operations, and that's a common database analytic that I want to do. And I end up losing a lot of performance by trying to do that as a graph. So for all these reasons, we realized that a pure graph data structure, a pure graph database wasn't really going to hack it, and we needed to come up with some way to combine the two. So maybe we need both tables and graphs as data structures, and these really need to be foundational in the database or in the platform, because after all, you're going to do all your operations in terms of these data structures, and if they're not foundational, you're going to lose both performance and scalability. We need both table operations and graphs, right? I want to do selects, I want to do joins. They haven't gone away in the analyst's workloads, but I also want to do things like connective components and community detection and things like that. And those are graph operations much more easily expressed, especially in semantic graphs where the edges and the nodes have attributes and it's just not connectivity. They're much more easily expressed and operated in terms of graph algorithms themselves. And so really, I need some sort of combination of both relational databases and these graph and knowledge databases that are beginning to emerge. But do we need new query languages? Well, no. We just actually can provide some extensions to SQL and get everything we need at the graph level, and that's what we've done. Do we need disruptive platforms? No, we just need to integrate new features into a relational database or into an existing graph database in order to do the mixed hybrid analytics that we want. And we really don't need to disrupt workflows, right? We can provide you with a graph database capability which builds on top of SQL and integrates with your SQL workloads. Okay, so let's just look at sort of the language piece here because we don't have a lot of time. So here's the Berlin benchmark, which is a Sparkle benchmark. It's used in order to benchmark RDF and graph-based databases. And you can produce the data in terms of RDF triples, which is the standard sort of Sparkle input. But you can also produce SQL data tables, all right? And we want to, again, we don't want to disrupt what people's workloads are, so let's look at what we can do if we had SQL tables which represent the Berlin data set. So we can ingest these tables and use SQL commands in order to define the schemas on these tables. And if we squint real hard in there, we actually see the edges that we would want in the graph view, or what Berlin would, what an RDF triple database would produce, okay? So there's a producer field in that product table or that product node, right, which is actually an ID which points to that producer node, okay? And there are all sorts of edges, right? There are edges here that go from the review to the product and from the offer to the product. And so there are fields in those tables which are actually the edges in the graph, okay? And they're self-edges as well. And there are some edges that sort of pass through a secondary table here where I've got a product in that product type table. Here I've got an ID which points back to a product and an ID which points to a type. And so this table actually is the edge which would go from the product to the type node, okay? So in the tables themselves, the edges exist, and now I just need to give you a syntax or a way to express those edges and express the nodes. And that's what we've done by extending SQL with, we call it GraQL, and we've extended it with constructs to declare vertices and edges, to describe graph patterns, and to return the queries of a result either as a table or as a graph. Okay, so I don't want to get into a lot of syntax because it never presents well, but here I create a vertex called product vertex. The key is the ID for the product, and we define these vertices as the rows in the table product. So for every unique row in the product table with a unique ID, I'll form a vertex in my graph for that entity. And then the columns of that row would form the attributes of that vertex and be available for the graph algorithm to pursue. Similarly, I've got a vertex product vertex, a type, and a feature. Okay. So that's just an example of the two vertices, product and producer. And then to create an edge, I, again, just have slightly new SQL syntax, which allows me to declare an edge called producer. It has the vertices, product vertex and producer vertex, and then it describes what the link is between the fields of the two nodes in order to create the edge. Okay? So very simple extensions to SQL, which allow you now to define a graph view of your tables. Okay. And I can have recursive edges in this case. And I've maintained all the SQL-like table operations, right? So I can do ands and ors. I can do selects on the tables. And so I can can define very complex vertices, which are a combination of the different rows and attributes or the entries in the tables. One of the nice things about being able to identify these vertex types and these edge types is it sort of partitions my data, partitions my graph into sort of homogeneous entities, which then I can exploit when I do data layout and operational schedule tasks for different operations. So it pays an advantage in the back end when I'm looking at executing, laying out graph data or a graph view of data, as well as the operations on a large cluster. Okay, I'll go through some examples here. And so with these definitions of the vertices and the types, I can create this graph view of the Berlin benchmark data, and this is exactly what a RDF platform would create from the RDF triples that would be ingested. Okay, and we save the table data as tables, just like a SQL database would be, and then we create hierarchical index tables in order to create the graph views. All right, and the index tables then give us very fast access to the rows in the tables, and therefore the attributes of both the vertices and the edges. Okay, so now to define or to program a graph walk or a graph query, again, we've extended SQL here in order to represent this pattern that we want to find. So we want to find product vertices of a particular product. So the idea is set to this string, and then we want to follow all its feature vectors, feature edges to feature vertices, and then follow back edges from the feature vertex to another product that shares that same feature. So here I want to identify, all products have similar features to this product here. All right, and so to do that, we've just developed a syntax where we can say from the graph, I want to start with product vertices which have an ID equal to this string. I want to follow forward edges to go to feature vertices, and then I want to follow back edges from that feature vertex to other new products. Okay, and again, I've maintained the SQL format for typing things. Then I accumulate all those IDs into a table, and then I can just execute some very simple SQL table operations in order to do group bys and counts and things like that. So rather simple extensions to SQL with a very nice, I think, succinct syntax which describe this pattern that I want to find. The SQL version of this query is somewhat much more complex. The Sparkle version of this query is much more complex and sort of unreadable, I think. And particularly this red code or the red lines there actually correspond to this sort of more intuitive, I think, description of the pattern itself. Okay, so we can do much more complex things. Again, we maintain the SQL table operations and the ands and the ors, so we can do branches. Here we have a pattern with multiple branches, and we represent that with a number of AND operations. And we support a number of edges. We have out edges and in edges. We can have conditional edges where the pattern continues if the edge exists. If the edge doesn't exist, then the result is returned as is. And we can also do not edges, so a pattern where an edge does not exist. Am I doing on time? Good. Okay. So with that now hybrid data model with graphs and things, we've developed a graph engine called GEMS. It's the second generation of it. The first generation was a scalable engine that based on RDF and Sparkle, and that we scaled that up to 256, 512 nodes on a cluster system, and we were doing graphs in the orders of 100 billion edges. We've now retooled that and redesigned it for both tables and graphs. So we're blending relational and graph data representations and methodologies and queries. We're providing an application programming interface for custom applications. Supporting data feeds that supply data in batches, so we're doing batch updates of the data. And again, the table graph view makes that, simplifies that quite a bit. And we're also serving a range of user profiles from application programmers to matter subject experts. The GEM stack is sort of conventional. So at the bottom we have commodity clusters, a thin layer of MPI to provide communications. The key on scalability in graphs is providing a very lightweight, heavily multi-threaded shared memory view thing. So this is sort of a software implementation of what the Cray XMT is. And then on top of that, we have a library of the data structures as well as the different algorithms for both the tables and the graph methods, and above that we have C++ APIs that you can program in directly, or the custom application and GraQL layer above it. So fairly traditional stack, and the key really is the GMT layer, which provides this scalability across clusters for both table and graph data structures. Okay, so then on top of GEMS, so that's nice. So now we can do some searches and queries, but really people are interested in knowledge graphs and the ability to do much more complex sort of workflows. And so we have another project at PNNL which has developed a knowledge graph platform called NOUS, and this starts with ingestion of starts with ingestion of either Wikipedia pages or plain text, right? So it goes through a natural language processing component, which extracts out facts, does entity disambiguation, identity clarification, and predicates, so identifies events in those facts. It then does a sequence of link predictions, inferencing, and things like that. It builds a big graph, and then provides a very English level but in the future a GraQL layer for people to do complex analytic workloads. So the features here is it can incrementally construct knowledge graphs from streaming data in multiple sources, so both streaming data and static data. It supports advanced trending and exploratory questions, so it can identify trends that are emerging in the data, such as what the hot topics and things like that. It automatically can generate hypotheses and guide users to information and discovery, so it can alert you to anomalies in the data, interesting facts, things that are peaking and diminishing, and it has a web-based interactive UI on top of that. Here's just some of the things it does. I may not go through these, but it does continuous pattern discovery, search, and reasoning. So this automatic thing of realizing what the current state is and what the emerging new states are. Detects new entities and relationships. So it does a good job of entity disambiguation, which is a key step in anything. It tracks provenance, so it keeps track of what was touched and who touched it. And then it provides the user with the dynamic checking of verification and learning and maintaining dynamic rule-based acceptance or rejections of facts. It provides confidence levels, so it may compare a number of times that it sees a particular fact or particular relationship and multiple different documents, and provides a certain confidence tag to each of the links in the relationships, which then can be further exploited when you do your analytics in order to return results or conclusions with a certain confidence. So the ingestion part is probably, where lots of things need to happen correctly, and so this is, so here we're based on Stanford Core NLP and the OpenIE standards, and we add a layer of heuristics to minimize the noise and the triples, so again, trying to get out sort of the confusions. It does a good job of trying to match keywords, so there are many different ways in English to say, manufacture. The company can manufacture something, you can produce something, you can deliver something. And those are all probably the same, same fact, and so you don't want to create an entity for each of those, but you want to be able to coalesce all those verbs, all those predicates, down to the same sort of word, same sort of relationship, and then represent that once in the database. And so that's a key thing that this does in parsing from the natural language into the graph entities. Then, as I said, it goes through a number of intermediate steps to process the raw triples, entity disambiguation, event detection, and relationship discoveries, and out of that it builds a large graph, as well as saves the dense data for those things in tables, so that we can then use our hybrid data model in order to build out the graph data structures and represent the data internally. Okay. All right, so I'll just go through one example and then conclude. So let's say we have a bunch of data in the database, and we sort of want to find out all the news about autonomous drones, and so that might be something we might ask the database. And it'll search through its representations, right, and pull out sort of a view, right, of everything that has the keywords, autonomous drones in it or associated with autonomous drones. So it ends up producing basically a view of the data, which is, constrained to facts about autonomous drones. And then, we may want to ask, well, what are the capabilities of these drones? And so again, due to the ingestion of the many documents across multiple data sources, there'll be links and edges in that graph which link autonomous drone entities to different capabilities. Okay, so we may pull out the fact that this Phantom here can perform autonomous flight as a capability of this particular drone entity, and then this particular capability. So then we may want to ask, well, what software components does this entity or these entities that can do autonomous flight have? And again, from other documents that we've merged in and processed, we may get the fact that this Autopilot is an open source and award-winning platform that autonomous drones that can do drones that can do autonomous flight have as a key component. And then which vendors are mentioned with Autopilot, where do they, who produces them? So we come up with this fact that this company Arduino here is a vendor that is associated with Autopilot. They're located in Italy. And then, Amazon, sells these systems that execute Autopilot. So again, these are all documents that we've ingested either from Wikipedia or from blogs or whatever. We've processed these. We've created this large knowledge graph of the information pertained in these documents. And then we produce, then we go sort of through this analysis process, and with different combinations of methods and algorithms. And because we've ingested these documents with this information, we can sort of navigate through this and come out with information about autonomous drones, their capabilities, software components that they use, and then who sells hardware products for those to execute those software components efficiently. So I'm almost out of time. So in summary, big data is changing our world. Exactly where we are on the Gartner hype curve is unclear. I would say that we're still sort of on this side of the hump, but we're certainly getting to a place where there will be a sort of culling down of the companies and the technologies that are supporting big data. At least from our experience, we feel that the winning platforms here will be support a variety, tightly integrated variety of graph and table methods, and they'll need the right data structures to do that. PNNL, we've developed both an in-memory scalable table graph engine, GEMS 2, able to support close to trillions of vertices and edges. We've extended SQL to find graph views and queries so that we don't have to disrupt current workloads. And we can provide both these table and graph views and operations. And we've built a knowledge graph capable of processing 2 million web crawls and analyzing trends in the data that it processes. Just contacts for all this for GraQL. Daniel Chavarria has been the primary designer of that. The GEMS project is now managed by David Haglund. And NOUS was designed and developed by Sutni Chaudhary. So if you want any information, you can contact me or any of these people. And there were, on the slides, there were a number of publications, citations as well. Okay, so thank you. Take any questions?